Let me get in right.
All right. What time is it? It's
10 already started.
Oh, thank you. Who did that? Who's recording?
Oh, I am Ben.
Ben. Ben, okay.
Thank you.
You're gonna work with. Oh shit.
Yep. I'll make sure Cheryl gets the right information.
Work with Cheryl and Phil to give you permission to post that, or she will.
Yeah. Will do. Can do. Will do.
Thank you.
all right. I think we might usefully start. Anybody want to say anything before we dive in? Okay. So again, thanks for coming, everybody. We talked about things with nature of wave functions and what that translates to in terms of dependencies of things like spectral lines on charge and quantum number. And now we're going to take a step towards still looking at atoms in isolation, but looking at some more of those kind of relationships and looking at what happens when you have more complex atomic structures. And I'll try to guide you through some simple scalings again to help, you know, understand where we're going from one place to the next. Because this does get mathematically quite involved if you let it, and that I don't want to let that get in the way of understanding what's going on. So, and the other thing I want to talk about is the interaction of the radiation with the atoms. And so we know from Maxwell. So I'm going to come at it from 2 points of view: classical and QM, and as usual. It's kind of what usually happens is we end up understanding things in a sort of bastardized sense, in the sense that you never come at it from pure classical mechanics, because it doesn't really work for these kind of small interactions with atoms and stuff. And you never come at it from full QED until you've got beyond where I am in this subject. So it's a mix of the two, and we end up talking about things like rates of transfer, about different kinds of radiation, but they all come down to one thing, and that is that we know that at least in classical mechanics, acceleration of charges leads to radiation. So, and then because we're dealing with the nature of the very small, we have to deal with quantum mechanics, and so instead of a plane wave description with its k vector and its two orthogonal states of electricity and magnetism that comes out of Maxwell, we have this idea of quantization, and it's called second quantization, where you represent the state of the photons by occupation numbers. I'm not going to go into that in any detail at all, because it's a huge subject, and it's, you know, things like Dirac, Feynman, these kind of people from the middle 20th century developed on this stuff. But I'm just going to point out how the interaction actually works. So as we know, as a quantum system evolves according to what a thing called the Hamiltonian is, which corresponds to you write down the classical expression equivalent to the Hamiltonian, but using the quantum operators. And so we have a Hamiltonian for the charges. That's just the atomic Hamiltonian. And then we have a Hamiltonian for the radiation, which works on these second quantization. And then we have an interaction between them. And it's this interaction that is easier to understand. And so what's usually done, and in the pedagogical stuff that I was introduced to at college, you have an interaction term which works out to be, when you write down the Hamiltonian, it boils down to sort of two terms. One is the photon gains and losses due to the interaction of the momentum operator and the vector potential of the radiation. It just turns out this is true. And the vector potential is the thing that's going to vary with e to the I k z minus omega t. That's what we are going to treat. So that's going to be treated classically in the simple formulation, and then that product turns out to be something like I to the k r, and that value of that kr will determine it's a number that's smaller than 1. So what it means is that the exponential term boils down to 1 plus kr squared divided by 2 factorial, etc. And this expansion leads something to called the multipolar expansion, which we'll talk about in a moment. I'm not going to talk about the second order term there for the moment. And so to go to the sun, then directly from quantum mechanics and classical mechanics into something like the sun, what we'd end up talking about is the classical mechanics modified or corrected by things like quantum mechanics, and you read things like gaunt factors. So this is a fudge factor that tells you where you went wrong with the quantum mechanics because you didn't treat it, and instead, after the fact, you say, well, classical mechanics gave me this answer, whereas we have to put in a gaunt factor. The other thing that'll be familiar to you is the oscillator strength. The oscillator strength is a classical concept where you just wiggle a dipole around, and the corrections to that from the quantum calculations are called oscillator strength. So you have one strength for an electron oscillating, and then you have individual oscillator strengths corresponding to things like individual transitions like Balmer alpha, Lyman alpha, etc. Okay, so the classical physics works really well with some corrections in the following cases. You have things like Bremsstrahlung radiation. That's important at X-rays, and it's important in radio wavelengths for the sun, for instance, for reasons which hopefully will become clear. Sometimes the gyration of the electrons in a magnetic field will also lead to radiation, and significant radiation, and these things are called gyroresonance, and in relativistic cases, synchrotron. And so gyroresonance is a phenomenon that's very familiar to radio astronomers. It has been for many decades in the sun. And then, of course, we can accelerate particles through electric fields, such as flares, and you can end up with radiation as a result of those kind of things. So now, but the tricky bit, the bit that's this uncomfortable situation where we're trying to fit, the ugly sister's shoes into Cinderella's slipper, is that we deal with quantum mechanics, but as astronomers we tend to be a bit lazy. And so what we end up with is a corrective picture, and we end up with all this terminology, which is really sort of junk. I mean, an oscillator strength is just a fudge factor, right? I mean, but we do have this. The quantum mechanics can be seen explicitly in the sun through black body radiation. I mean, it's obvious that that will arise from things like the modified classical physics, the free process. So electrons moving around thermally inside an enclosure will lead to black body radiation. And we know it's quantum because of the UV catastrophe that was discussed 100 and odd years ago, which meant that simply if you just integrated up all the classical models, you get an infinite amount of energy coming out of this thing. And of course, that's not the case. We have the distribution function of black body is that for bosons. All right, and then we have bound-free transition. So what's this? We know this is the sort of fudge language we're using. It's all to do with emission, absorption of radiation. That's all it is. And we talk about things like photoionization and recombination. That comes from Einstein's photoelectric effect. That's all it is. I mean, a photon comes in, and it's got enough energy to send one of the electrons out of the potential well of the atom, and it goes off. And the reverse process is radiative recombination. So that what happens is you need a photon going in, and then you need and that will photoionize, and then that in the opposite process, which we'll talk about later, is recombination, where you have an electron coming in, being grabbed by the atom with the emission of a photon to conserve energy, and also things like angular momentum. But then we also have this other class of things called bound transitions. So we know that in atoms, the quantum states that we end up with, these eigenstates, these long-lived states, they're very sharp, which means that they have a narrow distribution of energy in the spectral lines emitted by these levels. And these levels, therefore, are by definition sort of long-lived. So if you want to perturb an atom in the n=1 state of hydrogen, that sits there forever. So it's infinitely sharp, according to the uncertainty principle. The higher levels of hydrogen, say n=2, 2p level, decays quite quickly, but it's still very sharp because that lifetime is actually very long compared with what would be needed to broaden this line to make it look like a continuum. But these are all qualitative statements, and so this is the basis for which I'm going to move forward. And let's look at some simple ideas here. Just start at the beginning. So these are experiments from the 1920s and so, or 1900s, and so we have two kinds of radiation here, and this is X-ray data, and that's the middle of that figure is 0.6 angstrom, and so we have two kinds of radiation. One is the whale shaped thing underneath, and the other one are the two spouts coming out of the whale, and the spouts are these line spectra. And I'm not telling you anything many of you won't know, but just we're starting systematically here. Now, one of the really fun things about spectroscopy was that and it's sometimes easy to forget these things. If you take the wavelengths of different materials, so you thump a metallic or atomic substance source with high energy electrons, say, just from an accelerator, and then you look at the spectra, and then you make a plot of, for each atomic number, say Z equals 26 would be iron, and then you just plot the wavelength of the strongest line you find in the spectrum in the X-rays, and then you plot it as all those, for all elements, as a function of Z, and you can see there are some missing at the top, some of those rare radioactive elements for obvious reasons, and then there are things missing in between, which were things like noble gases, which was hard to shoot with targets at the time, as used as targets for excitations. But what you see here is a remarkable thing about spectroscopy. From one measurement, suddenly Moseley could complete the periodic table of the elements. Now, if that isn't a scientific amazing thing from spectroscopy, I don't know what is. So let's continue, and we're going to jump in, but I'm going to reinforce these later. So but here is an example of something of an abundant element, carbon, which lies which is abundant both on the Earth and on the Sun. It's about 10 to the minus 4 or something, 10 to the minus 3.5 of the abundance of hydrogen. So there's quite a bit of it around. And this happens to be a picture of the quantum states of some of the levels of an ion of carbon that has had 2 electrons removed. So it looks like a beryllium atom. And at the bottom, you'll see that there's something called a singlet S state. That's a closed shell. That means it's got no spin and no angular momentum. So that's like a billiard ball. I mean, it's just sitting there, and the only thing on its own that it could do would be to sit there unless it was hit by something else in the universe, and it might respond. Now, if you look at this, you'll see that that level has connections to other levels with these lines drawn. The solid lines are what I call permitted transitions, and there's one at 977 angstrom. So if you look at the spectrum in the UV below alignment alpha, there's a very strong line there of this particular transition. And this, in fact, was observed by the SOHO spacecraft, the SUMA instrument, back in, I think, 96. And they observed the whole sun with this, and it was so strong in a sensitive part of the detector, it left a permanent imprint on the detector. So this is a pretty significant thing. And if you look at the amount of radiation coming out of this, it's maybe 1 or 2% of alignment alpha. And when you get enough of these things, they add up to a lot, and you end up producing the ionosphere. Now, that one has a particular kind of transition. It's a 2s squared to 2p transition. So now I'm starting to use the jargon of, so we have an n equals 2 shell. Remember, n equals 2 means that there are certain number of nodes for a given angular momentum in the radial wave function. And for a given angular momentum of the electron, each individual electron, L, it has that number of nodes varies. But the n equals 2 to n equals 2, that would be completely the same level in hydrogen in a non-relativistic case. But now it's split because we've got multiple levels in the atom. Also, if you just go up from there, you see 2p to 3p. Now that's a very much larger energy. So we've got 3 times the energy by going from n equals 2 to n equals 3. So what that means is, if we look at where this ion is formed in the solar atmosphere, I've drawn a bar on the left called KTE, which is the sort of average energy of the electrons, where this thing likes to hang out. It happens to be in the transition region. I could have chosen a corona, whatever we want. But what you can see here is that KTE is about the same as the N977. So that transition, which has no change in principal quantum number, is about the same as KT. And that's a characteristic of most of the solar UV spectra and X-ray spectra. The strongest lines belong to N to N, not N to N plus 1. Now, what that means is, providing we have a Maxwell-Boltzmann distribution, we would be able to use the ratio of 386 to 977 to tell what the temperature of the plasma was. Now, if we assume we have a Maxwell-Boltzmann, then we can have something and say, well, look, I measured the electron temperature in this plasma by looking at the ratio between 977 and 366. And these have been done again and again and again and again in using various UV spectrometers. But you see there's a slight worry here that actually Tom Bogdan here was talking about before we got started. And that is, assuming a Maxwell-Boltzmann distribution is rather a severe constraint, given that we don't know how the energy gets into this part of the atmosphere that's radiating above the photosphere of the sun. And so what are the chances of it being Maxwell-Boltzmann or not? Well, we don't know, and we still don't know. And there's still debate as to what something like the ratio of these 2 kinds of lines is going to tell you. The next thing I want to point out is there's a dashed line with an even longer wavelength, at twice the wavelength of 977, going from a triplet state to a singlet. Now, what I mean by that is, in the singlet states, the electrons are spins. The spin part of the wave function are happily sitting there with opposite spins. They like to go together, so they're strongly bound in the potential of the Coulomb field of the nucleus. Whereas these triplet ones, the spins are parallel, and then they don't want to be in the same state, and so the energy is raised a bit because there's almost a net force as a result of these 2 particles having the same spin that comes purely from relativistic effects. What that means is, to us, is notice again that KT is about the same, but what it means is, I've drawn a dashed line there, is that in order for that to radiate a photon, you have to change the spin from triplet P to singlet S, triplet to singlet. It is a P to S like the other one, but now we've got to change the spin. And of course, in non-relativistic cases, the spin part reacts to the magnetic field as opposed to the electric field. So this is a much weaker transition in a non-relativistic plasma. And in fact, it's so weak that it can be collisionally hit before it can radiate. That means that we have a line here that could be sensitive to the density in the plasma as well. So I could take 977 and 1908, take the ratio and say, well, if I've got the temperature right, and you can use other lines to try and figure that out if you like, then we can also derive some quantity of the mean density of the plasma. This is the kind of thing that I started talking about 2 weeks ago. So there's the resonance lines, delta N equals 0. The energy is about KT or a bit above. Here are the other lines in the far UV, EUV, in which the energy required is much bigger than KT, so there are very few electrons in the Taylor distribution that can excite that thing. And then here is the spin forbidden transition, again with no change in principal quantum number. So this is a good example of how to remember when somebody says, what's a temperature sensitive pair of lines, what's a density, why are they sensitive to density? Hopefully that introduction will come here. Now this is a horrible looking thing, and I definitely don't want you to focus on this at all. It's just for completeness sake, in case you want to come back. The idea is that this is the interaction term in that potential that we wrote down here. So this is the V term. And here are the ways that it's expanded. And one, as I said, you have the wave as an e to the ik dot r minus omega t, and those are listed on the right-hand side of that big term at the top. You have an infinite number of multipolar kind of transitions that result from expansion of that and from the magnetic part of it as well as the electric part. And generally speaking, if I look now at the second row here, we have an expression for the magnitude of that interaction, namely the strength of the line between two wave functions, say the psi h on the right and the psi l on the left. This could be the singlet S state in the previous graph and the singlet P state. We know it's an electric dipole, so L, the little l is 1. So therefore, we can now figure out what this thing looks like. And it goes as the it turns out to be a bracketed term. The interaction between the light and the atom between those two states is now just basically a quantum bracket term with a little r in between. So it's a dipole transition because it's 1 power of r. The magnetic dipole, as I said, is the one underneath. And there you can see the angular momentum operators, because it's the magnetic part interacts with the magnetic field, and so the spin angular momentum interacts through the Bohr magneton with the magnetic field, and so the Hamiltonian, but that's so much weaker than the term above, the electric dipole. So, and as a result of this, and these come from, so there's some very elegant mathematics here. There's a little bit advanced beyond usual undergraduates, but the power of something like group theory comes in, where you have representations of a system in a very simple way, which leads to things like selection rules. So, for instance, if we go back and we look at this 977 transition here, we have a 2p to 2s transition. That's the parity, namely on the change in the wave functions as a function of reflection about one axis, is different between those two levels. And that's exactly one of the things that's needed for the transition to occur. And in fact, all those transitions shown there have a change in the parity. So they're all electric dipole, yes, so they all have an electric dipole component, but the one from the spin forbidden is not, has zero. The dipole operator does not act on the spin term, So we end up with a smaller oscillator strength again. So basically, we go back here. We have very strong lines, the resonance lines. We have a strong line for the higher resonance lines, if you like. We could go up to NP here, and then we have a set of weaker lines. But imagine now putting one of these, exciting one of these higher levels up here. This has a bunch of permitted lines. And even though there would be transitions down here between these triplets and this one, this is going to decay primarily via electric dipole lines. In other words, we only need to worry about these lines in the very lowest configuration of the atom. The rest of them are all permitted lines. So it's a great simplification that happens there.
May I ask a naive question?
Sure.
On your previous slide, you were saying that you really don't want to necessarily make the assumption of Maxwell that it has a Boltzmann distribution, because that's not necessarily a good one.
Well,
Assume.
you have to worry about it.
You have to worry about it.
Yeah.
Is there any information you were saying, for instance, you really need higher to get to the n=1. You need higher energy radiation around to make that happen.
Yep.
Is there any way you can use some information on the lifetime of the states or the strength of the line you're seeing to try to glean what's going on in that distribution?
Yes, indeed. So what Joan's asking is there a way, in a practical way, to use the relative intensities of the two lines? I introduced the simplest possible case and said, assuming it's Boltzmann, then you can see that the ratio of these 3p and 2p transitions down to the ground state will tell you about the temperature of that distribution function. But if there's a departure of that, say in a what are those called, kappa distribution, which is a truncated series of things that in infinite terms would lead to an exponential to the Boltzmann distribution. So they belong to the family. The Boltzmann distribution is the infinite term belonging to a class of these distribution functions. They would have a different shape. And the characteristic shape they have is the core of the distribution is more or less the same, but the wings get much stronger. And these are seen in space plasmas, and there are physical models that can explain why it has to have those particular shapes. People like Fran Bagenhall and others, people talk about these kind of things. Okay, so there's two ways of looking at this. First is to assume it's Maxwellian. Then the only thing you can do is derive something from the Maxwellian, like temperature and density. Or you can say, well, let's try and use it to find out what the shape of the distribution functions actually are as a function of energy. And so far, you can see that's going to be a tricky thing, right? We look at the sun, we're looking at a finite volume, maybe a megameter by a megameter by a megameter.
Right.
And if you've got a mix of temperatures in there, you can't tell the difference between that and a non-Maxwellian distribution. That's the problem.
Thank you.
So there's some faith involved here in what you're doing, but providing you make your assumptions explicit, that's perfectly good science as far as I'm concerned. All right, so I don't want to scare you to death, but these are the multipolar redshift transitions, and you can see what I haven't talked about is the nature of the wave functions to the extent of angular momentum and the quantum numbers associated with that. Because angular momentum is conserved, we have various rules about how, for an isolated atom, various rules about how a redshift transition, if it loses a photon is a boson and a spin 1, and so you've got to conserve the angular momentum of the whole system going from one state to the next, and so it's natural that you end up with changes in the total angular momentum of the atom. Remember, these atoms are a sum of electrons moving around a nucleus, but they also carry with them in an orthogonal space this thing called spin. So the reason these look complicated is simply because we've got like two manifolds in which we have to conserve angular momentum between them. And there's no point in memorizing this. This is just for, for your reference. Now, one of the really interesting things about the spectra that we see very often in astrophysics is that there's a relationship between the average temperature of the plasma and the ion stage. So how many electrons are removed from the atom in that plasma? And it turns out that in plasmas that have been allowed to relax to almost an equilibrium state, so that they don't evolve, they're just sitting there with an input of heat and they're radiating, then there's a relationship between the mean temperature and the ionization stage. And that relationship basically says that, and I'll go back to our reference figure here, that KT, see this? KT is always a factor of 10 smaller or so than the ionization potential. That just comes from some work which I'll get to later. Coronal approximation is one of those things. What this means is something that we have a very specific regime. We don't have to worry about huge populations in these three and other levels. And I'm talking here about thin plasmas, not the photosphere or the chromosphere. The thin plasmas are, even though this actual relation is the same for all. And I'll give you an example. So this is about 10 to the 5 Kelvin, this KT, and this line is formed at 4 10 to the 4 or 6 10 to the 4 Kelvin, roughly the same, but it has an equivalent ionization temperature of about 6 times higher than that. That's very, very typical. What that translates to is we don't need to worry too much about these high-lying levels. They decay very quickly because they have a strong electric dipole transition, a tendency to fall down to the ground state or to the triplet state. So we have decays down to the singlet state or the triplet, 2p triplet state. Okay, this is familiar to those of you that have looked at helium. If we were to translate that to iron, and I go back to iron again because it's the most abundant spectral species in the sun, both in the photosphere and elsewhere. So let's look at the photosphere. The ionization potential of iron is about 8 electron volts, but it forms in a plasma at, say, 5,000 Kelvin, which is 0.4 electron volts. So again, we find that the iron atom, a neutral ion, is formed in a plasma where the ionization potential is about 10 times the thermal conditions in the sun at which it's formed. So this is a really nice way to remember this. Okay. So that's that yellow statement there. This also means that because those highly excited levels are mostly out of the reach of most of the Boltzmann distribution, usually only one electron can be excited at a time. There's one really important exception, which we'll get to before the end of this. And so what this means is the strongest transitions in the spectrum occur between the lowest levels, okay? And this is exactly what, for the example there, is precisely the one I talked about just now. And so really, when we look at the spectrum of these ions, unless we want to look at something very special, like the distribution function that Joan was talking about, we really have to look at things like a few electric dipole, magnetic dipole, and sometimes electric quadrupole transitions. I'm not going to talk about those. That's just an extension of the multipolar expansion to the next multipole order too. So, and again, in the higher levels, only electric dipole transitions need to be considered unless we have very high, highly charged ions. So if we have, say, uranium with 91 electrons removed, it's a hydrogen like uranium. Imagine the energy of that state being 91 squared times the energy of hydrogen. That's moving very fast, that electron, to stay in that potential well. And it's going to have almost relativistic speeds. What this means is, as we go into relativistic conditions, electric fields and magnetic fields start to become part of the same phenomenon, which means that there's no longer the separation between the magnetic dipole transitions and the electric dipole. So you tend to get all transitions in those kind of atoms of many orders. Okay. Now, again, this just summarizes what we talked about. And I said I would reinforce these ideas again for you so that we don't lose track. And so that summarizes all that. Now, so let's look at what happens if we put that atom and we look at the same number of electrons. So there's beryllium. So there's 4 electrons sitting around a nucleus, and now we just plot it as a function of nuclear charge. And what you see here is something that's a slight departure from what I told you. What I told you was that the energy of the formation of this ion is usually about 1/10 of the energy of the ionization, which is up here. This starts to change a bit as we go towards the corona. So these are exactly the same electrons, the same electron configurations. We have and down here we have a weak central field compared with the interaction of the electrons. We've still got 4 electrons, but we've only got a 4 times, a charge on the nucleus of 2, whereas here we've got a charge on the nucleus of 10. So the amount of force due to the potential field of the nucleus is much stronger than it is of the electrons themselves. And so all these levels that are split by the electron interaction, electric field interaction between electrons here, start to converge to a very narrow region. And so what that means is it translates to the fact that suddenly all these different transitions have roughly the same wavelength. See that? That's just very nice, because what that means is we got transitions of different character, electric dipole, multipole, all in the same wavelength region, which means that we can build one spectrometer. We don't have to look at 1500 angstrom and then at 300 angstrom. What we can do is we can look in the soft X-rays, and we find all these transitions all bunched together at the same wavelength. And that's what they did with things like SMN, the spacecraft, looking at the soft X-ray region. And there are these very nice diagnostics, which were found, in the spectrum of flared in particular. And these are listings I put in places for you. These are going to be important, but we'll come back to them. These are some of the words we use to describe the evolution of this quantum system embedded in a plasma. So we have spontaneous decay, we have stimulated emission. These are all words familiar to you. We have absorption and then re-emission called scattering. We have something called redshift. These are all words we just use to talk about the evolution of the full quantum state of an atom in the environment of electrons. Why am I not talking about atoms in the environment of the ions? Well, the ions are really slow. For a given, again, Boltzmann-like distribution, we've got something that's for hydrogen, protons move 40 times slower, or 43 times slower than the electrons. So and they have the same charge as the electron. So what that means is that the rate at which a hydrogen atom is going to influence the electric wave function of the impacted atom is going to be about 43 times slower. And now if you go to very heavy atoms like iron, it's 56. It's going to be the square root of 56 times slower than that. So basically, to first order, we can consider the atoms, as far as their radiation is concerned, being impacted by a sea of electrons moving around with static ions. That's basically the notion that one has. So these are all just what I would call, I put it in quotes here, collisions with photons. They all involve an H nu at the end, okay?
What is stimulated recombination?
It's the same thing as stimulated emission, but with two photons coming in, impacting a single S state and creating a double S state, with a photon and a free electron. So it's knocked a photon off.
Oh, thank you.
I mean, that's a very unlikely thing to happen,
yeah.
Right? Because you need two photons and a particle. And this is a very important part of the thing as well. In most bright plasmas we see around stars and stuff, we have an essential imbalance in that if we you have one electron coming in and knocks an electron off, imagine the reverse process of that. Then we have the same electron that's just bounced off, but we also have the free electron that's knocked off. They come together and then they recombine, and then you have one electron. That involves the collision. The first process involves the collision between two particles. The second process involves the collision between three particles simultaneously, which is a much rarer event. And so you have an imbalance between these two reversible processes. And so by definition, it cannot be in thermal equilibrium. Okay. But also, when you look at something like corona, you only have to worry about two body processes, right? So that's a great simplification. In the photosphere, that's not true. The density is so high that something like, two electrons coming together and hitting an iron 1 atom, iron 2 atom, and recombining is balanced by the opposite process. That's called LTE. So that's why we have a non-LTE versus LTE kind of thing. So this is again something to remind you of what we're talking about here. These processes show up in the spectra. So here again we have recombination spectrum. So we have those smooth curves with edges on them. That's just a collision of a hydrogen atom in a 1 atmosphere plasma inside a laboratory device. And then it has these superimposed lines, just like in the X-rays. Okay. So what's going on here is we have the two kinds of radiation, the photoionization, the so-called continuum radiation, and we have the radiation occurring between the two bound states. And as we go to more and more, the wavelength scale is going to remain the same here. So we go to hydrogen, you can see the Lyman edge is near 900 angstrom. Now we go to helium, so now we've got exactly the same electronic structure, modified by these effects of relativity, so that the various splittings and things have changed, but the overall structure is the same. Now that edge is around 304 angstrom. Now we go to hydrogen like carbon. Now that edge is at 35 angstrom, and you've got a bunch of lines around 40 angstrom. These are the ones observed with things like SMM. And under those conditions, various interesting things happened. And I'll show you some examples later of, you see a line that's caused by something called dielectronic recombination. You see a fully forbidden J equals 0 to J equals 0 transition, and things like this that result from conditions in these atoms which favor very different kind of a departure from the electric dipole, very weak magnetic dipole, electric quadrupole, everything. That ordering starts to not mean much anymore, and you get into a fully relativistic case where things get mixed, and you end up with very different looking spectra. Here is oxygen. Again, now we're down at 20 angstrom for the edge, and we're seeing these are the Lyman-like lines of oxygen, which are very famous in the and very good diagnostics of things like abundance changes in the flares, during flares and things like this. Okay. In the last few minutes, I'm going to try and, I think many of you will be vaguely remembering that when you have more than one electron, of course, things get complicated. We talked about that with carbon-3 and the beryllium sequence. Helium is a very nice pedagogical thing because it's the first departure from analytically available solutions. But more than that, we have to take into account the fact that the electrons are fermions. We have what we call exchange terms, and we end up with things like the spins aligned, which means triplets or orthohelium, and the spins opposite, which means spins in opposite directions, means we have singlet states, so there's no net spin. That's like a hard billiard ball. And because of the electrons liking to be in opposite states, the energy of the triplet levels is much higher than the singlets. So what we'll look at here is the structure of helium briefly, and I'll finish with something called H-, which is a bit of a surprise and a very important thing in the sun. Okay, so here we go. Again, I've plotted the average KT where helium lines are formed. Helium is not observed in the solar photosphere. Okay, it's because, look at that, it's 20 electron, the first excited levels on the left axis are 20 electron volts above the ground state. Okay, so that means that we have a ratio of 20 to 0.4 electron volts in the photosphere, say. That's a factor of 50. So e to the minus 50 is the likely LTE population of those levels relative to the ground state. So helium is this weird thing. It's like it is a noble gas, and the other noble gases are exactly like this. They have no delta N equals 1 0 transitions. You've got to pull the thing out of the potential in order to get the triplet states and the excited singlet states. You got no choice. That's why the energy is so big. So just like helium doesn't interact with anything around us, and you can inhale it and talk like Donald Duck or something, you know, it doesn't interact with this plasma very much either, and it's the same chemical reason. It's very hard to excite these states, and that ground state is a singlet S state, which is like a billiard ball again. So you can just breathe it in and breathe it out. Tiny little billiard balls don't do anything. Okay. So what we're looking at here is the two systems, the one in which the first transitions we see in energy are in the EUV. So we have a 304 angstrom line, the Lyman alpha line of helium. It's at 304 angstrom. It's incredibly high energy. And just neighboring that, the triplet system, just like in beryllium, the two exist. So that's with the spins opposite, the left-hand side, and then when you put the spins together, the energy is raised so much that we end up with a first transition being our very one of our very favorite transitions, which is the 10-830 line of neutral helium, occurring between the N equals 2 levels of the triplet P of state and the triplet S state. Okay, so what's going on here is that we've got two separate systems that almost don't talk to each other, except if we were to imagine getting some population up here by some high energy phenomenon, like a high temperature or photons coming down from the corona. Remember, these orbitals here are very, very big, very high end. See that n equals 20, right? That means that the collisions between this term and this term are going to be very large, enormous collision rates. But the same thing between this and this, to a lesser extent, because it requires exchange of spin. And to exchange spin, we've got to do something like penetrate the wave functions with the impacting electron and swap the electrons around. So it's a slower process. It's not a long-range interaction. It's a short-range interaction. But it means that, you can equally populate these things. So this is one of the subtleties of this thing. But I mean, look at this. This is the energy of the chromosphere, the top of the chromosphere, say, the bottom of the corona. Again, this is about 20 times that. So helium is basically, if you have a Maxwell distribution function of all the particles, it's almost impossible to excite helium. And some 40, 50 years ago, Hal Zirin, an infamous guy here in HAO, then pointed out that, well, because of this high energy needed, perhaps it's coming from photons. And so you have photoionization. And this was actually proposed much earlier by people like some of the famous astronomers of the time. What's her name from Harvard?
Cecilia Payne-Gaposchkin.
No, it was after that. I'm talking about, who's the guy behind the OSO series?
Leo Goldberg.
Goldberg, stuff like that. So the point is, helium then is exactly what Joan was talking about 20 minutes ago. It's a very good place to look for tails in the distributions. So helium is sensitive to tails and distributions, which is great if you're interested in looking at unusual things. But if you're interested in just thermal things, which I think are less interesting, then helium is no interest at all. So what this turns into meaning, I'll turn it around and say, in our plasma, if we've got some high energy things going on, like a very strong electric current owing to a tangential discontinuity or something, and the electrons are whopping along and suddenly they impulsively release energy and heat, then the jump in temperature can very strongly change the distribution function and raise the wings and suddenly show up in a line like helium that wouldn't otherwise be visible in something like calcium-2 or magnesium. So maybe I'm saying too much here, I don't know, but it kind of ties together. So here are the helium-like spectra again. Again, computed in the lab, and here we go with carbon, and that's neon. And again, look at the soft X-rays. These are all triplet and singlet transitions. Because the charge is very high, the difference between electric and magnetic dipole is smaller. We've got relativistic effects mixing up these states. So just in this region alone, we've got lots of transitions with very different sensitivities to temperatures and densities, which is why it should be observed again, I think. Okay. Let me show you why. So here's a very nice article. This is really groundbreaking research where they had to look at, they had some early rocket spectra and stuff. And what the first sentence says it to me, the recent identification of 2s triplet s to 1s singlet s line from helium-like ions, blah, blah, blah. That shouldn't happen, right? I mean, it's got no, it's the same parity, it's got the same, it's got a change in the spin. But remember, we've got, these are in ions of things like iron, heavier ions than helium, which means that relativistic effects are very strong. So if we look at what is actually going on here, it's fascinating to see that, again, this is our same old beryllium-like ion, but one shell down. So instead of a 2s squared electron, like beryllium had here, we got 1s squared. So we got 2 electrons around an oxygen atom, which has got 6 electrons removed. Okay, so what's going on here? You see the resonance line is that big one in the middle, the longest lines. So we have collisions up and radiation down as we had before. That's at 21 angstrom. But close by, at wavelengths of 21.8, we have the triplets down, and they're almost as strong as the resonance lines, so they're easy to observe. But look at that, you've also got a J equals 0 to J equals 0, and you've got radiation from the chromosphere exciting from the metastable level, which is the 1s2s electron. That's sitting there. That can have that's the lowest level of the triplet system. That can build up some population. So now what you've got is you've got a bunch of lines which are totally unexpected on the basis of what we learned from simple hydrogenic atoms with a low charge. But when we should not have not expected them, because the relativistic effects really kick in and start to change the nature of the transitions in these atoms. And lastly, before we go away for the week, I want to talk about this beautiful thing that happened in the 1930s. Cecilia Payne, as we mentioned at the beginning, really started astrophysics and in particular the astrophysical spectroscopy on the right foot. Until then, there was a lot of guesswork going on, and they thought the sun was composed like the Earth. Okay, about 10 years later, there were things talked about at things like Solvay conference and very famous things going on at the time of Dirac and Einstein and Bohr and all these people. And one of the biggest puzzles turned out to be that the models that they had made for the sun, around this time, they had developed a theory for the chain reactions needed to power the sun. So the nuclear proton-proton chain of reactions that determines why the sun can live so long and radiate in the way it does, that was all pretty well understood. And they had a way of describing the transport of energy out. And they developed the interaction of the radiation with the plasma so well that they could model quite accurately what they thought the spectrum of the sun should look like. The problem was it didn't look like this. It's at about 6,000 Kelvin, and the calculations done at the time couldn't get that temperature low enough, and it was a really enormous difference in the computed and observed spectrum. So, like all people with a good imagination, somebody called Wilt proposed that, well, helium is very strongly bound. I mean, you got 20 electron volts of potential well to climb out of before you can remove one of those electrons. It's got a charge of 2 in the nucleus, and it's a neutral thing. Maybe what happens if we just look at the quantum mechanics of a nucleus with 1 charge and try to put 2 electrons around it? When I put it like that, it doesn't sound too bad, right? I mean, you'd think that, okay, and in particular, when you have 2 electrons whose spins are anti-parallel, that means they like to be in this state. And whereas if they were parallel, they'd be at much higher energies in a region which is unbound, which means you don't have an atom of that kind anymore. So when you have 2 spins aligned like this, oppositely, then you can actually glue things together. And it's the battle between the electron interaction term, which is just the potential given by E squared over R1 minus R2, versus the central field. And it's the aligned spins and the which allow it to bind this thing together. And it has one bound state. But how can it be stable? Well, it's because of what I just said. The electrons are fermions would like to be together, spin up and spin down. They can happily be nested down there. The consequences of this are even visible in the thing I showed you a couple of weeks back. That box shows you a change in the nature of the solar spectrum. And that change is due to a change in the main way in which electrons and photons interact with H minus. One is called bound free and one is called free free. So it's the change. The free free is simply an electron going past the hydrogen atom as it stands and then going off to another state that's also, but it emits a photon while doing so, and it's lost a bit of its energy. So what we have here is a clear signature, and this signature is seen here And if I show you the difference between what was expected at the time, here we have H minus. So we come down here and we know that oops, there should have been a little Planck function plotted there, but it's disappeared. The brightest part of the sun lies in this region here, right? Almost all the photons are in this region at around 5,000 angstrom, down to 3,000, and then it tails off slowly up here. Notice that there's almost no opacity here. This is the amount of blocking of the light by photoionization of magnesium, and this is now the photoionization of H minus. This was missing. And you can see here, this region I've highlighted here in the infrared is way the hell down here. This is now plotted in reverse. All the abundant elements are at UV wavelengths when they have being photoionized. Uniquely, H minus is photoionized from its only bound state. It's just at the right energy to absorb most of the radiation at the surface. And so suddenly, all the calculations became into agreement and showed that the sun spectrum really is a sort of inverse of that Planck temperature there. And at that, I think I'll stop.
What do you think the percentage of H minus is?
The actual amount of H minus, I don't know what that is. It's relatively small. And that's a good question too, because in the photosphere, it's quite hard to ionize these elements. So things like sodium and potassium, which is even lower, that's where the electrons come from, but there aren't many of those elements around. So you've got 10 to the 4 times as many neutral species as you do electrons in the photosphere. So there's very few electrons, and now but there's a lot of neutral hydrogen, and if the electrons are grabbed by the neutral hydrogen, and then photons come and try and remove it, that's the process which I just described. You know, that's a fairly rare event, but it's such a dominant cross-section and such a strong, highly abundant component, and a sufficiently abundant component of the photosphere, that it suddenly all this stuff. So without this kind of spectroscopy, we would not understand astrophysics and nuclear synthesis. I don't think. We might know something about hotter stars, but the sun would still be a puzzle without the ingenuity of these people.
Very cool. I never knew that.
Is there a lithium minus ion where you fill up 1s and 2s completely with aligned spins?
I'm sure there is. What the bound state structure looks like, I have no idea.
Yeah, I just wondered if
you can have a lot of negative ions, and I showed some in the table from Alan at the beginning.
Okay.
But that would be shifted to the shorter wavelengths where there aren't as many photons. I assume, maybe I'm wrong with my assumption. We're pointing out that this can happen where there's a whole lot of photons available.
Yeah.
So I'm not saying it can't happen.
yeah, I just wondered if it's possible.
So if you compare a lonely electron sitting around an atom, so that all the other electrons are sort of bound underneath it, and you've got one electron left, like sodium, potassium, then an electron could come along and pair up with that and make a negative ion, because the two spins can be opposite. And there's no coincidence that chemistry follows these rules. This is chemistry, actually. Chemistry is the dynamics of electrons around atoms or molecules. It's all the same stuff. So as soon as you did in your chemistry lab, you learned that you throw a piece of magnesium or something in a flame or something, or into water or whatever it is, you have a strong interaction where you put some helium through it, and absolutely nothing happens. I mean, it's the same stuff here, just reflected in the radiation from the atoms, as opposed to the chemistry of the atoms. Exactly the same. So next, I'm tempted to skip the really complex atoms, but this is sort of what I'd like to talk about and show you. I showed you some of these before, so again, some reinforcement for next time. But really, I'd like to get into how we deal with quantitatively embedding atoms into plasmas, things like SAR-Boltzmann, non-LTE, coronal approximation, trying to understand the relationship between the plasma, the thermodynamics, and departures from thermal equilibrium, things like this that are important for some of these spectra that come out. I absolutely adore this subject because it's quantum mechanics at its heart. And while I don't understand quantum mechanics, you can use it, and it's so beautiful to see the world opened up on these microscopic scales like this. I mean, it's just ridiculous that we can understand with JWST that apparently these galaxies being formed at the beginning of the universe. They shouldn't be there. I mean, that comes from spectroscopy and just gathering broadband light as well. I mean, that requires a lot of faith, right? That the physics is the same there as it is here.
Mm-hmm.
But there's no proof that either way. How would we know that the physics are different? I think we would. But I don't know. Maybe we fooled ourselves into a corner. I mean, I assume that very clever people have asked that question and come to the conclusion that we can't tell. I don't know.
So the big takeaway message is that aligning your spins because they're fermions has a huge effect on levels and structure and things like that. And
it goes a bit further than that, in that then that's why you get the periodic table.
Mm-hmm.
There's that's a characteristic of filling up
a shell.
Available shells, and those shells are like hotel rooms. Once an electron is checked in, you can't check into the same room. You've got to go to a different one, and so that's why it's periodic.
You mentioned LS coupling, and there's also JJ coupling.
Yeah.
And when do you use one and when do you use the other?
So JJ, okay, so what is this? This is when you couple two, you've got a multi-body system, each with components of angular momentum. They operate in two orthogonal spaces that are, at least for non-relativistic atoms, fairly orthogonal, but they do influence one another. And so a complete quantum state has to be a function of position through the Coulomb interactions, but also of multiplied by a component which is in the spin space. Okay. When you add a certain electron that has an angular momentum of say 1, so the 2p electron, I'm drawing a picture of it going around a hydrogen atom, but that's a classical case. I don't know how to visualize this. And then you add it to it a spin, so it's now, and it's basically uncoupled. Now, if I add another electron in there, then what I've got to do is find a way to evaluate the total angular momentum. Well, the total angular momentum is very clear. It's the sum of all the angular momenta.
And there's 4 of them now, right? There's the 2 orbital and the 2 spin.
And so if there's no coupling between the spin and the orbital space, then the 2 orbital angular momenta line up appropriately, and then you add in the 2 in an orthogonal space for the spins. And that's called LS coupling, and that's an approximation when you have a many electron atom. It's an approximation even with helium, but it happens to be rather good. It breaks down when the linking between those 2 spaces becomes stronger. And eventually, and that can happen because of relativistic effects. It can also, and so what happens there is that complex atoms can surprise you sometimes. And when you couple the angular momentum like that, you end up with a very particular spacing between the levels and a very clear pattern in the spectrum. 1 to 2, something like this in the wavelength differences or something like that. JJ can change it completely. It can turn it upside down, alter the order of these things. And that's when the spins of its electron, of one electron, coupled so strongly to the L of that electron, that forms an angular momentum vector itself. And then the other electron does the same. So you have a J and you have a J. But that requires that the interaction between the spin components and the individual orbital components is now stronger. You can see it's a perturbation, right? A perturbation thing. You could start with LS and end up with JJ. And you can see that happen along isoelectronic sequences. You can see the energy levels get closer together, and then they start splitting apart again as a function of Z. So the exact same transition. All you've done is change the nuclear charge, but the chemistry turns out to be quite different as a result of these physical couplings. And there's also JL. There's pairing of electrons. I can't remember what that means. Whether there's zero angular momentum in the orbits and then they just pair up. But I think superconductivity is an example of that pairing.
Mhm.
Yeah. Don't you love physics? I do. I mean, it's much more interesting than solar physics. Anybody, any comments? If not, send me some messages and let me know how things are going. I went a bit quicker this time, I think, which is what Tom asked for. So please do let me know. It's for you.
That's great. Oh, yeah.
Okay. Thanks, everyone. See you next week.